Today we're going to continue looking at convergence of series, and we're playing the multiple choice game. We want to determine if a series is absolutely convergent, conditionally convergent, or divergent. But while we're doing this exercise, we want to, at least in our mind, explain what it is about the series that helped us decide, and what test will we use were we to be called upon to prove our results. So let's take a look at this first series. The sum of n squared plus 3n plus 5 over n cubed minus 2n squared plus 7n minus 10. So what do we think is going on here? Convergent or divergent? Absolute or conditional? In this series, what we want to notice is the important term on top is an n squared over an n cubed. So we look at this and we can immediately see this is divergent. We've answered the most important part of the question. We know that this diverges. This diverges because when n is very large, the only thing that matters on the top and the bottom is an n squared on top and an n cubed on the bottom. So we could do a comparison, probably a limit comparison, because I don't know how this actually compares to 1 over n, but this is a 1 over n. We would compare this to the series 1 over n, which diverges. Let's think about the series. 1 over the square root of n plus 3. Once again, we want to try to get away from all the things that are getting in the way. Like this plus 3, when n is very large, that doesn't matter. So we're going to do a comparison with 1 over the square root of n. So we might think this diverges. It's rational. Rationals and radicals should all be compared with can all be done with the comparison test. So this looks like it diverges. We'll compare it with the p series, 1 over the square root of n. And this is a p series with p equal to 1/2. Which is strictly less than 1. So diverges. If we look at a variation of this, it's not the individual problems that we do, it's the changes, and that's where stuff happens. So if I change this to a minus 1 to the n, if I throw in the alternating on this, we know that the series without the alternating diverges, but the terms still go to 0. And so if I throw alternating on top of that, now we can get conditional convergence. So we're thinking that the 1 over the square root of n diverges, but the terms go to 0, and alternating will get us convergence. So the terms go to 0, and the alternating gets us convergence. So in this case, we have a series that we've seen before, 2 plus 3n over 7 plus 5n. Here we can see the limit of terms is 3/5, so the series diverges. So this one's simple to take care of. Your Honor, I present this evidence. Limit of the terms is not zero, therefore the series diverges. Let's suppose I take this series and make it alternate. This problem is me trying to be very sneaky. Oh, these things are multiplied, so I'm not trying to be sneaky by writing it weird. So here's your instructor trying to be sneaky. So something diverged, but if I make it alternate, that makes it converge, right? Nope, this one still diverges. The limit of the terms now doesn't even exist. The alternating doesn't matter because the terms don't go to zero. So in this case, the limit of the terms, the limit as n goes to infinity of 2 plus 3n over 7 plus, oops, I forgot the alternating parts. The limit as n goes to infinity of negative 1 to the n times 2 plus 3n over 7 plus 5n does not exist. It goes to positive 3n or negative 3/5 or negative 3/5. So it's not getting closer to anything. So on one side, and then on the other side, it's going to negative 3/5. So it's not approaching any one value. Since the limit of the terms does not exist, the limit of the terms is not zero. And so the series diverges. For very large values of n, this series just starts looking like 3/5 minus 3/5, plus 3/5 minus 3/5, plus 3/5 minus 3/5. And because there's an infinite number of those things, there's an infinite number of those terms, we don't get zero. For a finite number of 3/5 and minus 3/5, we would get zero. But for an infinite number, we can't say. So the point of doing this exercise is to say, don't just start throwing conditional convergence on things where you see alternating. Don't let alternating draw you into convergence that isn't there. Don't let alternating just make you automatically say conditional convergence. That's a common thing that students fall into. Alternating, that's when we have conditional convergence. That just happens to be when the alternating shows up more often. It's kind of like when you're doing an algebra class. If you spend a lot of time factoring polynomials, you'll walk out of your algebra class thinking that most polynomials are factorable. Because every time you had a quiz with 10 polynomials for you to factor, only one of them wasn't factorable. So you get this false impression about the factorability of polynomials just because most of the ones that you encounter are factorable. But the reason that most of the ones that you encounter are factorable is because your instructor wants to give you practice factoring polynomials and not just a random collection of polynomials. Because if I just dropped 10 polynomials on you at random, none of them would be factorable. Because the probability of pulling a factorable polynomial out of the pool of all possible polynomials is zero. It's the same as the probability of pulling a rational number randomly from all the real numbers. There's just not enough of them around compared to the number of the real numbers. Don't let alternating make you think conditional convergence, because then you're acting, you're just trying to imitate the things that you see. Here's another favorite 1-2 punch. So we know that the series 1 over n squared converges, and all the terms are positive, so we get absolute convergence. Oops, not delta convergence, absolute convergence. We get convergence with the p, it's a p series with p equal to 2. And 2 is strictly greater than 1, therefore we get convergence. All the terms are positive. That gives us the absolutely convergent. So before we hit the alternating series test, we weren't concerned with the kind of convergence that we were getting. We were just getting up or down, converge or diverge. But now we're trying to decide when something converges, is it absolute or conditional convergence? So series 1 over n squared is absolutely convergent. The thinking would be the series, it's a p series with p equal to 2, and 2 is greater than 1, so therefore it converges. Since all the terms are positive, it's absolutely convergent. Note that all the terms are positive, not because of the square, because all the n's that we're plugging in are positive. So then, if we want to be sneaky, I follow it up with this one. And this is the same test where I don't want you to let the alternating make you think conditional convergence. Because this series, if I take the series that I had 1 over n squared and I make it alternate, it's still absolutely convergent. I get the stronger condition. The alternating is not what makes this series converge. This series converges in absolute value, so it's absolutely convergent. On one hand, it's easier to see why this is absolutely convergent immediately following 1 over n squared. On the other hand, psychologically, it's difficult because the -1 to the n makes you think conditional convergence. It's not the alternating that's getting us convergence here. It's the 1 over n squared. 1 over n squared goes to 0 fast enough on its own. We don't need alternating to get us convergence. We did need alternating to get us convergence when we were looking at 1 over the square root of n. 1 over the square root of n does not go to 0 fast enough. We needed the alternating to get us convergence. We do not need that for 1 over n squared. Any questions?
Professor, could you explain that p series part again? The p equals 2 is greater than 1.
So a p series converges. The series 1 over n to the p converges if p is strictly greater than 1. That's one of our results of the integral test.
Got it.
The series 1 over n to the p converges for p strictly greater than 1 and diverges if p is less than or equal to 1.
Thank you.
This is one of the ones that we don't have. This one we could justify with the integral test, but it's common enough that we should just know it. So think about the integral test. Think about the integral test to get us the p series. When we add 1 to the exponent, if p is greater than 1, then n is still in the denominator. So if p is greater than 1, then when we integrate, the antiderivative will still have an n in the denominator. And so when n goes to infinity, the n in the denominator will make that term go to 0. So those first 7 problems, those first 7 were all variations on the on rational and radical, and the thinking that goes behind when we see those. What we want to be able to do is start introducing some other types of terms. So let's see, where were we? 8. So we also have to be able to recognize, excuse me, other kinds of series. So here we have 5 over 3 to the n. This is geometric. We have 5 and then a 3 to the 5 over 3 to the n. So this is geometric, and all the terms are positive. I suppose I should tell you where I'm integrating or where I'm summing. So this is geometric with a common ratio of 1/3, which is less than 1. Notice that the 5 is not being raised to the n, just the 3 is being raised to the n. So we know that this series is absolutely convergent. So it's geometric with a common ratio of 1/3, which is less than 1, and all the terms are positive. So that's what gives us convergence. All the terms are positive, and that gives us absolute convergence. So that's how we get those parts. The test we introduced yesterday was the ratio test. And the ratio test is giving us the idea that factorials are going to be bigger than exponentials, which will be bigger than polynomials. So factorial growth above exponential growth above polynomial growth. So if I start adding things, so instead of 5 over 3 to the n, what if I have 5n squared over 3 to the n? So this is no longer geometric. The n squared means this is no longer a geometric series. So this series is not geometric, but we can compare it to a geometric series. Or since it's got this exponential part, we could use the ratio test. And the ratio test will give us absolute convergence in this case. I know the ratio test is the new test. The ratio test is the new test, but if we run a ratio test, the limit from the ratio test will be 1/3. Which is less than 1. So it's not a geometric series, but the geometric part of the series is giving us absolute convergence. And the ratio test gives us absolute convergence anyway. if we flip this over, if I have 3 to the n over 5n squared, now we're going to get a series that diverges. This is just a reciprocal of the previous one, so the limit from the ratio test is going to be 3 rather than a third. So what we're doing is not actually running the ratio test, we're seeing what will happen. In the ratio test, the ratio test will ignore anything that's polynomial, like this 5n squared. And so we're just going to be looking at the limit as n goes to infinity of 3 to the n plus 1 over 3 to the n. The 3 to the n cancels out and leaves behind a 3. So that'll be the limit from the ratio test. Once again, we're just trying to develop the site, the Eldritch site that allows us to look at a series and decide if it converges or diverges. So since we're on the topic of the ratio test, we should start thinking about how factorials compare to things. And now I've got this 3 to the n. In example 10, 3 to the n was winning. It says, I will take these terms to infinity. And the 5n squared can't keep up. But now the 3n squared on the top that wants to go to infinity is fighting with an 1 over n factorial. And in the numerator, we might have a billion copies of 3, but we'll also have a billion factors down in the denominator, and we're starting off with a billion. So in the numerator, we have a billion copies of 3. In the denominator, we have a billion factors, almost all of which are greater than 3. So the denominator wins. The factorials win. This one diverges. The limit from the ratio test will be 0. Oh, wait, sorry. I didn't flip it like I intended to. The denominator is winning, so we'll get absolute convergence. Usually when I do this, I flip these, and I put the 3n back on the bottom. So the limit from the ratio test with the n factorial in the denominator will be 0, which is less than 1. Then if I flip this over, the one I intended to do, we just have the reciprocal arguments. Now the limit from the ratio test is going to be the reciprocal of 0, which is infinity. Not really, but close enough. So this one diverges. This is very casual. This is fine to do in casual conversation, but don't bring this kind of argument. Don't say infinity is greater than 1. Because if you get an overly pedantic judge, then they're like, well, I see that you're making this infinity is greater than 1 comparison, but infinity is not a number, and we shouldn't be really using it with a greater than or less than. And you know, it's like super pedantic. And you're like, oh, dude, you know what I meant. But you kind of open up the door for someone that's super pedantic to seize on this one casual thing that you said. And use that against you. At which point you should just be like, oh yeah, but the point still stands, right? You know what I mean? So all we have to do now is look at a bunch of series. This was only 12. This is hardly any. This is only 12 series, but look at a series and we want to decide quickly if it's absolutely convergent, conditionally convergent, or divergent. We want to be able to see that factorial is bigger than exponential is bigger than polynomial. This will give you a rough idea about what's going on. While you're doing this, you want to think about what is it that's making you make those decisions. Like this page, it was a bunch of ratio tests. Not because I'm running a ratio test, but because I see what would happen in the ratio test. This is what the ratio test is telling us: factorial, exponential, and polynomial. So that's how we're basing making the decision. It's great if we can write nice, complete, and concise arguments and use these tests to prove our results. But the most important thing happens when we look at the series and say this diverges. It's a factorial on top of an exponential. The factorial is going to win. The numerator is winning. This series diverges. The most important thing is to say this diverges. And 3n over n to the factorial, absolutely convergent. 5n squared over 3n, absolutely convergent. Those are the important conclusions that we make. It's results that drive mathematics, not proofs. I guess my engineer is showing right there. I was an engineering student for like a couple of years. But one of my favorite professors said, it's results that drive mathematics, not proofs. We spend a lot of time doing proofs, but the most important thing is the result. Any questions? Comments? Snide remarks? All right, that's going to do it for today. Tomorrow, we're going to start looking at the interval of convergence for a power series. So one of the things that you'll want to do is grab your textbook or open up a digital copy of your textbook and take a look at chapter 9. This is where all this stuff is found. And in the review exercises for chapter 9, at the end of the chapter, there should be a set of problems where it's in exercises 1 through 1000, determine if the series converges or diverges. So it'll just be a big chunk of problem. I don't think there's not 1,000. There's, I think, like 30. But one of the math student things you want to develop is the site for not only when something converges or diverges, but also when a set of problems is grind out some problems. And that'll look like in problems 1 through 1,000, do the thing. And then you just have to do the thing 1,000 times. That's right, tomorrow is a flex day. Tomorrow's the 22nd. Dates and times just don't exist anymore. So tomorrow's a flex day. So I'll see you all on Friday. Everybody have a good couple of days. And thanks for playing.